Now let's talk about conductors and insulators. Conductors are materials that electron can move freely through the material. Most of metals are good conductors. Insulators are materials in which an electron is bound to atoms and cannot move freely through the material. Now, examples of insulators are glass, rubber. So if we charge an insulator, because charge cannot move freely in this insulator, only the part we charged carries charge. Semiconductors are not good insulator, no good conductor, but we can add some other materials that carries free electrons, at least carry some free electrons to semiconductors, then they will turn into conductors.
Current flow or electron flow is possible only because electrons can be freed from their electrostatic attraction to the proton of an atom's nucleus. Electrons are freed when energy is applied in the form of heat, light, magnetism, or electricity. The electrons in the partially filled outermost shell determine the chemical properties of the atom. It is called the valence shell. Electrons in outer shells have higher average energy and travel further from the nucleus than those in inner shells. This makes them more important in determining how the atom reacts chemically and behaves as a conductor. The pull of the atom's nucleus upon them is weaker and more easily broken. In this way, a given element's reactivity is highly dependent upon its electronic configuration. It's the valence shell electrons of any element that are crucial for current flow. A material is an electrical conductor when one or more of its valence electrons can be easily freed. Most good conductors have one free electron in their valence shells. Good conductors do not require much force or voltage to free their electrons, thus propagating the flow of energy. The purpose of using conductors is to allow electric current to flow with minimum opposition or resistance. Copper has high conductivity. Gold and silver are also conductive, but they're more expensive and thus not practical in most applications. When electrical current flows in a good conductor, it creates heat or resistance. All conductive materials produce some resistance to electron flow. This resistance is reflected in the form of heat. Non-conductive materials, called insulators, resist electron flow. The important thing to remember about insulators is it takes much more force or voltage to get an electron to leave an insulator's atom than a conductor's atom. Even when enough force is applied to an insulator, only a very few electrons can be released at any one time. Insulators protect conductors from touching each other and protect us from touching conductors. Most materials other than metals are insulators. Plastic, glass, and rubber are commonly used good insulators. Semiconductors are elements that are unique in that they are neither good conductors nor good insulators. This characteristic can be advantageous. Semiconductors can be made to be partly conductive by mixing small amounts of impurities containing free electrons. This is a process known as doping. Semiconductive material, such as silicon and germanium, are the basis for transistors, diodes, and other solid-state devices.
We can charge an object by conduction. It means if we have a charged object and we place it in contact with another object, then some of the charges carried by the charged object will move to the object that is in contact.
During charging by conduction, some electrons pass from one body to another. In the presented example, electrons pass from the plastic pipe onto the metal rod and the leaf of the electroscope. As metal is a conductor, the charges spread across it. Therefore, the leaf of the electroscope is deflected. The plastic pipe, on the other hand, is an insulator. That is why, in order to transfer a greater number of charges onto the electroscope, we need to collect them from various locations on the pipe.
We can also have charging by induction, which means the two objects does not have to be in contact, but then we can induce charge in another object. And in the next slides, we'll see an animation to explain the process.
A conducting material contains within it electric charge that is free to move. The gray sphere shown here is a conductor that initially has no net charge. When the blue ball representing a negative charge is brought near, some of the positive charge in the sphere is attracted and some of the negative charge is repelled. The net rearrangement of charge in the conductor is indicated by the coloring of the sphere surface. When a conducting path to electrical ground is connected to the sphere on the side opposite the external negative charge, the negative charge on the sphere, repelled by the external charge, can flow off of the conductor. Removing the conducting path leaves the sphere with a net positive charge. When the negative charge is removed, the sphere retains this net charge. This process is referred to as charging by induction.
In most neutral objects, the center of positive charge and the negative charge are at the same location, so it doesn't exhibit any electricity. But if we put it near to a charged object, the positive charge and negative charge will realign or redistributed. And then, so the center of positive charge and the negative charge no longer at the same location, so that object will exhibit charge electricity phenomena. Like phenomena we are familiar with is that if we have a plastic comb, we comb our hair, and then we bring it near to some small papers. Because of this charge by induction, also called polarization, so the comb will attract those small papers.